Okay, let's get this show on the road. Hello, everyone. Hope you're well. Welcome to another edition of Math 1207. So, I guess yeah, I already typed this in the notes, but maybe I'll just actually do it now. So I posted a practice problem set for test 1 in Gradescope. So you guys should be able to see it. And I want to actually talk about that a little bit. So as you know, your test is on Thursday. It's going to be on Gradescope. And I just want you guys to get some practice actually using Gradescope. So I put some problems in a problem set. And so you can go in and you can have a feel for it. It's not timed, even though I put instructions in it and it says it's timed. I just want you to see what the instructions would look like when the test comes up on Thursday. So yeah, so there are instructions there that tells you all sorts of stuff and that it's timed and blah, blah, blah. You can kind of ignore that and just actually practice the problems. It's not comprehensive, the one that I posted. So this one that I posted maybe goes up to the beginning of trig substitution or something like that. But I just wanted to throw some problems together very quickly so that you can kind of get practice on Gradescope. And if you log into Gradescope, I don't know how many classes you have. This is probably the only class you'll see. So your class will be right here and you click on that. And you're going to see this test 1 practice problem set 1. I will be posting some more, but this is just one that I wanted to just rush out to you so that you can get started right away. I'll post 2 or 3 more, and the hope would be there would be more comprehensive, and maybe one of them would be like a practice test, like an actual mock test, where I'd write it to be the full length and cover the full set of topics that I actually want to test you on. And so I'll put up 2 or 3 more, but this is just one to get you started. And if you actually clicked on that, which I can't click on it now because it's going to show you the answers, but you'll actually see something like this. I did mention some of what I just mentioned here. It's not comprehensive and it's not timed. It's just to get you used to actually using Gradescope. But below that is kind of what your test is going to look like. So of course, read the instructions first. Now you're getting instructions ahead of time. So you might actually, if you learn these instructions very well, you can probably save some time and just skip over them later on. So here it's like, okay, you're going to have 60 minutes to do this, blah, blah, blah. You know, anything that has to show your work, you can upload a picture and all that stuff. And it gives you some other instructions there. So those would be the instructions. Of course, that's the honor code. You type your name here to say you won't cheat, and all that good stuff. And then you can get into the problems. Now for this one, I did, because there's going to be a mixture of problems. There's going to be some multiple choice. There's going to be some stuff that you can fill in short answer. And there might be some things that you check all apply. So there'll be different types of problems. And then there'll be some problems like this, where it says it will indicate at the beginning of the problem, you must show your work. So this means it's not one where you can just click something and move on. Some problems are like that, but there are some selected problems for which I would want you to show your work. And so I'll say, oh, you must show your work for this problem. Whenever you see that, that means you're going to write down what you think the answer is, write out your full solution, sort of how I do it in class. And then you're going to click to upload your work. You're going to click select files. You're going to upload, and then you save your answer. So every time you do a problem, you save your answer, just to be safe. And so for select problems, you'll do that. Not all of them have that. So like this one doesn't have that. Just click what the answer is. Or this one, the select all that apply, just check what the answers are that you want to put in, whether they're correct or not. Those wouldn't be the correct ones. These 2 would be the correct ones, but never mind. But yeah, so some of them, as you can see here, I'm just literally asking you to complete a rule. The actual test, I'm not going to have any problems like that. It's just like me trying to, give you something to do and actually make sure that you do know some of the basic rules. Like I do expect you to know like what is the integral of that? Well, probably not so much that one. But this is a basic rule. You should know that. Like this, you should know. You should just be able to click on what is the answer. And then there are a few where you have to like show your work, right? But while this test isn't comprehensive, I think it goes up to like the basics of trig sub. It's just something that will get you used to the feel of using Gradescope, as well as just used to the feel of what taking a test would be like. So you can do that. Like I said, this isn't the only one I'm going to post. I'm going to post some more practice tests. But this was just one I wanted to rush out to get you guys actually working on something and sort of seeing the kind of problems I would ask you, for example. So that should be something that you can try out. It is up until July 21st, 6 p.m. I believe which is, it's the start of our class on Thursday. So anytime between now and Thursday, you can log into this, do some problems. It's not timed, so you can log out and come back. As long as it hasn't hit this date, it's not going to, you can enter and leave as many times as you want. Now, when I do put a timed practice test in, it's very important to you to know, once you actually open it, the clock will start. And so you would have an hour at most from the time you open it until whenever the end date. So for the other practice tests, I'll still put this as the end date. They'll still end before our class on Thursday, but they will be timed, which means if you open them today, 1 hour from when you open them, you won't be able to enter that test anymore. It'll be like, it'll lock you out. It'll be like a real test, just to get you used to the timing factor. So yeah, the actual test is going to be around an hour, hour and 15 minutes, maybe an hour and a half if I want to give you some extra times to upload. But as it's not quite in the instruction, but it is a recommendation that I would have here. When you're taking the test, you can actually log in from 2 places. So I would recommend that you log in on your phone, at least on the first one, because you can just there's an option that when you click upload on your phone, on your mobile device, it'll give you the option to take a picture right there. Just line up, make sure it's right side up, everything. You take your picture and then you can upload right on your phone. I think that's the quickest way to do it. Students who sometimes complain about running out of time, it's because they'd write on a piece of paper, they actually scan it, and then they try to upload it. Too much work. Like if you have a smartphone, that's going to be by far the quickest way to do it. You just take a snap a picture and then upload directly. So you can actually do that from your phone. If you let me finish and then I'll get to your question. So if you log in on your phone, and you can upload from your phone, but let's say you don't like squinting, your phone screen is too small, you can, in addition to that, log in on your computer, and you can, I would do something like that kind of setup, like have my computer to read off of, but then when I'm ready to upload things, just use my phone. And that's going to be the quickest way to actually do that. Question?
So, sorry, you kind of just answered my question, but we will be able to log in both on our phones and on our computers?
Yes.
With no issue. Okay.
Yes. Now, I do think, at least this was the last time I used Gradescope, this was the case. I do believe it's the one that you log in on first that's going to be the submission one. Like when you log in, if you log in on your phone, you log in on your computer. If you try to submit from your computer, it usually gives issues because it's going to be like, oh, there are 2 instances of this open, like only one of them is allowed to submit answers. And I believe the default one is the first one you log in on. So if you want to do that kind of setup, I would say log into your phone first, then log into your laptop, and your phone is going to be the main one to submit answers. Like the laptop instance won't. But you will be able to log in from 2 instances. So that's that. So yeah, like I said, it's not comprehensive right now. And I do ask some things here that I wouldn't ask in the real test. Like just basically asking you, oh, what is the basic rule for this, right? That's not something I'm going to ask you. Like when the actual test comes up, that's something I expect you to know. And so I'm not going to ask you about that directly. But everything else, like there'll be somewhere there's like multiple choice, might be some like where you have to fill in the blank, like here, integration by parts. What is the mnemonic used to choose the parts? Who remembers? What is it?
Liate.
Liate. So you just type in Liate and submit your answer. Right. So there'll be some multiple choice. There might be somewhere I actually just select all that apply. So you'd select this and not the others. And like I said, there are also some problems where I actually want you to actually write it out. So I ask you to actually compute this integral, write out, show your work. Want to make sure that you know how to write stuff out. And then you click here to actually upload your answers. So that's up. It will be up until Thursday. It's not timed. You can log in anytime and just try to feel around. I will be giving you additional practice problems to work out as well.
Quick couple of questions.
Of course, yes.
Will the practice test be graded?
No, they're not graded. They're purely for your practice.
Cool. And second question, if our real exam is going to be like an hour and a half long, how many questions can we expect to have?
It will be roughly what the practice exams are. So it'll be somewhere between 15 and 20. But not all of them is like long form, right?
Cool.
So there'll be maybe ones that you'd have to work out, like show all your work, maybe 8 to 10 such ones. And then I might ask you some other concept or short answer ones. And
cool, thank you.
So I would want to, I'll probably aim for 20, but maybe it might be a little less than that because I just want like an even number of points to each one. Oh, 20 problems, each one worth 5 points is an easy thing to do. You know, if I give like 18 problems, then each one is going to be like, what? It's good. It gets annoying. So, so somewhere around there. But in terms of things you'd have to work out, just assume you'd have to work out 8 to 10 of these problems, and then the other ones will be more concept. Kind of select all, apply, maybe fill in a blank, multiple choice kind of thing. Okay. And of course, until then, you can ask me questions. Before then, let's see. Right. That being said, let us jump in here. Okay. So this is yesterday's lecture. This actually, oh, someone's coming in. Okay, yes. Actually, it looks a little weird on my screen, not like it normally does, but okay. All right, so this was yesterday's lecture, so let's do a quick review. First, we played an integration game, which you can play with yourself or play with your friends, have fun with it, pick out random ones and try to do them. So we spent some time on that, but then we moved into improper integrals and we spent the rest of the lecture on this. And so basically an improper integral is just a definite integral, like integral from a to b of f of x dx, but it's messed up on one or several of the requirements that we need from the fundamental theorem of calculus to actually evaluate it. So fundamental theorem of calculus needs f to be continuous. It also needs the interval to be finite in length. However, for all sorts of reasons, your f might not be continuous on the interval. The interval might be infinite in length. There are many applications to actually doing that, and we want to figure out what integration looks like in these cases. The basic idea here is, and so that's what an improper integral was. It's an integral that where those assumptions break down. So either your f is discontinuous at one or more points in your interval, or your interval is infinite in some sense, meaning that your a goes down to negative infinity or your b goes up all the way to infinity, or even all of these might occur. We had examples where all three of these things happened. Now, of course, the basic method for dealing with such an integral is to identify the bad points. Infinity is always a bad point, and any points in the interval that you're looking at that makes your f of x undefined is also a bad point. And you're going to break up the integral so that there's only one bad point per integral, and then use limits to approach the bad points. So you replace the bad point with some variable, and you're going to take limit as that variable approaches the value of the bad point. And you're going to do the integral as you would normally do, but then take the limit afterwards. And if the integral converges, meaning it gives you a finite real number, and this happens for all the integrals, you say that the improper integral converges to whatever the sum of those numbers are. And if any one of those limits mess up, you say the integral diverges. So we did some examples of that. So sometimes you don't have to break it up because there's only one bad point and it's already exposed. So you can just take that bad point, replace it with a letter, and take a limit approaching it. There are times though where, like this one, you look at 1 over x squared, integrating that from negative infinity to infinity. Negative infinity is a bad point. Infinity is a bad point. Also 0 is a bad point. And so you can actually break the integral up from negative infinity to 0, 0 to infinity, but these have 2 bad points per integral, which is bad. So you have to continue to further break them up. The idea is eventually we want to plug in some limits here, but if I can't have a limit going to negative infinity and at the same time going to 0, that doesn't actually make any sense. So I need to break it up in such a way that there's only one bad point on each integral that I can approach with limits. Then I would go through, I would integrate using our rules and whatever technique of integration is useful in that scenario. Integrate, apply the fundamental theorem of calculus with the new variable. I'll get an expression in terms of the new variable, and then I take a limit of that expression. And that will, if it gives me an answer like 1 or whatever, awesome, I can say it converges. If I get like infinity or the limit does not exist, I would say it diverges. And if there are several integrals that you have an improper integral, you have to break it up into several integrals to actually apply this method. If any one of these integrals mess up, if any one of them goes to infinity or the limit does not exist, then the whole thing is messed up. The show is over. The original integral that we started with does not converge. Now, there is another scenario that sometimes the integral that we are dealing with is very difficult to deal with. So we might not actually be able to do the integration part. And in this case, the method is to actually use some sort of approximation method, maybe use a computer to help you out to get close to the answer. But you can actually do it by hand or do it by analytic means or whatever. Now that phase, we're not dealing with it in this class, but I at least want you to be able to identify, okay, if I have an integral, an improper integral that I cannot integrate, can I tell that it converges or not without actually integrating it? And the answer is yes. And a couple of the most powerful tools are the direct comparison test, or just the comparison test, which allows us to compare two integrals. And then based on whether one converges, we can determine whether the other one converges. So the scenario is like this. If I have some non-negative functions and their integrals line up in this certain inequality, 0 is less than or equal to the integral of f, less than or equal to the integral of g, then if the bigger one converges, the smaller one has to converge because it's always less. And if the smaller one diverges, the bigger one has to diverge because it's less. And you can't really conclude anything else in any other scenario. We also have what's called the limit comparison test. And for this one, you don't need to know who's bigger or who's smaller or any of that. It turns out if you take the limit of their ratio and you get a positive real number, then both integrals will do the same thing. So if you know for a fact that one converges, you can know that the other one will also converge. And if one diverges, you know that the other one also diverges. So those were the two comparison tests. And these allow us to talk about convergence or divergence without actually doing the work of computing the integral. In doing that, something that is often useful is this theorem that we spoke about, the integral from 1 to infinity of 1 over x to the p dx. This converges if and only if your p is strictly greater than 1. So if I'm integrating 1 to the infinity of 1 over x to the 7, that converges. 1 to the infinity of 1 over x to the e, that converges. 1 to the infinity of 1 over x to the 1.1, that converges. If I have 1 to the infinity of 1 over radical x, does not converge. 1 to the infinity of 1 over x to the 1/3 power does not converge, right? Yeah, I can actually know that it's going to converge based on what the power of x is. So this is actually a very important theorem because you can actually use this to compare to a lot of other integrals. And we actually used that to help us here. So, you know, we used 1 over x to the 997 to compare to 1 over x to the 997 minus 5, where the top one is very difficult to integrate, whereas the bottom one, very easy to integrate. And we have a theorem that tells us it converges. And it happens to be, well, I'm actually looking at an example for the limit comparison test. Yeah, this one with the +5, we want to know whether it converges, but it's very hard to integrate. But we can look at this one, which looks like a 1 over x to the p integral. And since we know it converges and it's larger, then the other one converges. If the middle one diverges, then the upper one diverges as well. And so those were the comparison theorems. And we did a few examples of that using comparison to actually talk about whether integrals converge. We also saw this nice little trick of introducing inequalities where there were none if there are trig functions, like, you know, your cosine of x is between -1 and 1. That's always going to be true no matter the context. So you can always just apply that, right? And see if it's helpful. Like, it's literally something you can always do. So if you see an integral that's very difficult and there's like a sine or cosine in there, you can start by bounding the sine and cosine between -1 and +1 and replacing them with some value between that and see, is that helpful? Usually you can build up to the original integral and that builds up an inequality for you right away. And then hopefully that inequality is useful. However, even if it's not that useful, you can probably even use the limit comparison test with the two integrals here. So that was another useful trick. And we had some, I believe 2 more examples. Yes, we had 2 more examples to get through. So that actually leaves us here. So yeah, I was saying before we finish up exams from last time, I was going to talk about the test here, but I already did. So I think I can actually just delete that whole thing. All right, so we are going to jump in and finish these last 2 examples. So before we begin, any questions? On improper integrals, or maybe anything I said earlier? Or just start continuing with the lessons. Okay. All right, let's actually just continue then. All right, so here is an integral. We have secant squared of x divided by x to the radical x, going from 0 to 1. And we actually want to know it's not one that we can actually integrate directly. So we're actually going to want to know, does this converge or diverge? And we're obviously going to want to use some sort of comparison. So one way we can go about this is, again, we can actually talk about what a boundary for this trig function would look like. Now, secant is a little bit so here we know that so note, we know, for example, that cosine of x is always less than or equal to 1. And so we also know that if you have two things, let's say, how do I want to say it? It's kind of sloppy writing this out in inequalities. Maybe the graph would actually be nicer. But the idea is cosine is, let's say it's strictly greater than 0. Let's not look at 0 because I don't want to. Let's ignore 0 for a second. When two things are on the same side of 0 and we have an inequality, then we know from pre-calc that if we were to take the reciprocal of both sides, the inequality would actually turn around. So this would kind of imply to you that your secant squared would have to be greater than or equal to 1, right? And of course, if you flip the other side, it's going to be like 1 over 0, which is approaching infinity. And it depends on where you are, but that would happen. So you kind of have this inequality built into secant. Another way you could see that, or from the graph, remember what secant is. It's 1 over cosine. So if I look at my cosine graph, which say is going to be this guy, so this is, say, y equals cosine. Then I know that secant is 1 over cosine. Now, obviously, wherever the cosine is 0 is a bad point because I can't take 1 over 0. However, everywhere else, it actually has this reverse relationship. So if I have like a number that's getting close to 0, like here, or maybe I should put, what color do I want to put for secant? Right, so let's say I have a very small number here. If I take 1 over that number, it actually gets larger. So if I plug in this point from the cosine and take its reciprocal, it's actually going to jump up higher. So the graph of your secant is going to have this, right? So when cosine is 1, secant is also 1. But as cosine gets closer to 0, as it goes down, you're taking 1 over a number that's getting closer to 0. And we know that if we look at like 1 over x as it's approaching 0, it shoots up to infinity. And so our secant will either shoot up to negative infinity or positive infinity when our cosine is getting close to 0. So with this in mind, you can either actually construct the graph of secant. And here you can see that secant is either strictly bigger than 1 or strictly smaller, well, not strictly bigger than 1, greater than or equal to 1, or it's less than or equal to -1. And then if you square that, obviously all the negatives, you ignore them. The negative parts flip up. And so this actually implies that your secant squared is always greater than or equal to 1. Okay. So in either of these sorts of ways of thinking about it, you can actually come away with the fact that your secant is actually bigger than 1. Your secant squared in particular is also positive and bigger than 1. So using 1 or 2, maybe I'll move this over a little bit. we see that I can take my secant squared, and I know it's actually larger than 1, but it's also actually larger than 0. Obviously, 1 is larger than 0. And so now what I can do is I can divide everyone by x radical x. So my 0 is less than or equal to 1 over x rad x, less than or equal to secant squared x over x rad x. So now I've constructed a set of inequalities for this guy. And this, of course, would imply, if I start taking integrals now, I have that. And so now what I can do is I can actually apply a comparison theorem. It turns out it's hopefully it's very easy to see that the middle one is going to diverge. Why? Because it's like you're taking the integral from 0 to infinity of 1 over x to the 1 plus a half, so that's x to the 3 halves. So this is like x to the minus 3 halves dx. That's going to be, you add 1 to the power, divide by the new power. And obviously, this is like minus 2 over radical x. Now I'm being a little sloppy here because I didn't take limits, even though this is improper. But obviously, if I plug in the 0 or take a limit as x is approaching 0, right? That undefined here. Limit diverges. Okay. So this is like a comparison theorem. It's like this part here is my integral of, I think g was what I did. This part here was my integral of f. And then over here I have this 0. So I can apply the comparison theorem. The integral that's less than the one that I care about diverges. And obviously this is improper because of the 0 in the bottom. So then I can say the integral diverges by comparison. Okay, but of course the idea is you look at this and you will realize that, hey, I can't integrate that. Or I'll tell you in the problem, I won't ask you to evaluate the integral. I'm just say determine whether it converges or diverges, which means you don't have to actually do the integral. Just justify to me that it converges or diverges. So I know I'm going to want to use some sort of comparison. So I can either use a direct comparison test or a limit comparison test. And in either way, in this case, you'd probably want to compare this to 1 over x to the rad x, but here I built up my inequality. It was actually the nicer way to do it. If you had the limit comparison test would be a little problematic here because of the secant squared. The limit actually won't converge. So this is a scenario in which the limit comparison test is probably has an issue. Because if you take like the secant squared over x rad x and then divide by 1 over x rad x, you flip it. The x rad x's would cancel, and so you just have a limit as x approaches infinity of secant squared x, which doesn't exist, right? Because this pattern sort of repeats, right? And it takes on multiple values between 1 and infinity. And so the limit wouldn't actually exist. You wouldn't be able to actually use the limit comparison test. But yeah, here we could use the direct comparison test, set up our inequalities based on what we know about trig functions. And that gets us the answer. Namely that this diverges. Do you want to? Even mention that. Because sometimes students look at these and they're like, okay, the comparison test, I need to work out inequalities and blah, blah, blah. Why not just ignore the comparison test and always just use the limit one? I can always just take the ratio and take a limit, right? And it turns out it's not quite true. We kind of need both of these. There are situations in which the direct comparison test will work, but the limit comparison test won't work. And yeah, in a Calc 2 class, often it's the other way around, but it doesn't have to be, right? So, and this is a pretty standard problem. I actually stole this problem from your textbook because it was an example in your textbook in one of those practice problems I asked you. So it's not even like, oh, I picked something way out of the ordinary that you'll never encounter. Like, no, this is a standard kind of problem. And the limit comparison test could not help you here. So if I looked at the limit as x approaches infinity of, say, secant squared x over x rad x over 1 over x rad x, that actually does not exist. So for the limit comparison test to apply, the limit has to exist and it has to be positive. Yeah. So this has to be true and that has to be true. So we can't actually apply the limit comparison test here. So yeah. What about this one? So for this one, same idea. Like you wouldn't want to have to integrate that. We don't really have anything to integrate that because obviously a substitution is not going to work. I would need like an x to the 4th, blah, blah, blah in the top for that to work. And it's a quintic polynomial. We can't factor that, right? This one doesn't have a nice pattern for us to factor. So you have the x to the 5th plus 2x plus 1. So partial fractions is off the table. Trig sub is off the table. Like there's nothing we can do with this guy. Like I can't integrate that. So now we want to talk about whether this converges or diverges without actually integrating it. And so now the idea is, once I know that's the situation I'm in, I want to think, well, what could I compare it to? So you see this guy, you want to use a comparison theorem. What is a nice function that you think you could compare this to? Any ideas, any guesses? It might be worth, this is kind of a hint, but ultimately our x's are getting very large. They're going off to infinity. So especially from some intuitive notions that you learned in Calc 1 when doing limits should kind of hint to you like what you want to actually compare this to. right? Like if you think of the limit as x approaches infinity, say, of this. What is that? And how would you know? And you shouldn't have to do a lot of calculations for it. You learn something in Calc 1 where you can actually know what the answer is here very quickly. Or at least tell me the intuition. Anyone knows? Any guesses at all? Well, the intuition is the largest ones will control the limit, and you can essentially ignore everyone else. Because compared to like an x to the fifth, say, an x is effectively 0 when your x is going off to infinity, right? The largest powers are going to dominate. And so you can actually ignore all the smaller powers. And so based on what the largest powers are doing, you can essentially determine what the entire limit is doing. So essentially, this limit is actually equivalent to just this limit, which of course is this limit, which you know is 0. But of course, you learned in Calc 1 that you have a ratio of polynomials and the degree of the denominator is greater than the degree of the numerator, and you're going off to plus or minus infinity. The answer is 0 always. So you learned that rule. The intuition behind that rule is that the bigger ones dominate. So you can actually ignore all the smaller ones. And just looking at the ratios of the bigger ones, you can actually determine what happens. Whether it will actually go to a finite number, that's if the degrees are the same. If we'll go to off to infinity, if the degree of the higher one is larger, and it goes to 0 when the degree of the smaller one is larger. So that sort of intuition would be what would kick in here. So you see this random improper integral, which you can actually integrate. My idea, of course, would be, of course, you'd want to use comparison theorem, but the idea would be, what do I want to compare it to? And the intuitive thing to compare it to would just to be compare it to these two guys where we ignore all the other guys. So nice function. Just look at the highest powers. Now, the nice thing about this is that we have a theorem that will tell us whether this converges or not. And we know this converges. Because our P equals 2 is greater than 1. So actually, no, that converges. So that's the first thing. Now, the idea is, how do we compare the original function? This is our x cubed plus x plus 10 over x to the fifth plus 2x plus 1. And the idea is this greater than or equal to, or is this less than or equal to the thing I want to compare it to? And turns out that this part here, at least, I don't know, you might want to think about it, but the idea is it's not obvious. Now, of course, you can probably come up with some kind of detailed argument for why you can know one is larger than the other. But at the end of the day, we know certain intuitive things are true about fractions. Like if you take a fraction, you make the denominator larger, the overall fraction gets smaller. Or if you make the numerator larger, the overall fraction gets larger. So here, if we start off with this, notice that we're making the top and the bottom larger by adding these guys. So by making the bottom larger, you've made the fraction smaller. But then by making the top larger, you've made the fraction larger. So you've done changes that affect the fraction in opposite ways. And it's kind of hard for you to know which one is going to actually win in the end, right? Now you can make an argument for, why the 2x plus 1 would be have a greater effect than the x plus 10, and so the denominator actually makes the thing smaller more than it makes the thing larger, and you have to actually discuss that and talk about it. But at the end of the day, it's not obvious. It's something that you'd have to put a lot of thought into, and I would say it's not actually worth it to put in that thought. So I'd say something like we've taken, x cubed over x to the fifth and have made now there are times when it's actually super obvious which one would win. In this case, it's not obvious. Like if you both made the denominator larger and the numerator smaller, like if these were both negatives, then it's actually obvious like who would win. But with the pluses, it's not so obvious. All right. So we've made the denominator larger, and the function gets smaller, and made the numerator larger, hence the function gets larger, right? So we've done something that makes the fraction smaller and larger at the same time. Not immediately obvious which one which change dominates. So whenever I'm in this situation where I all right, I got the perfect thing to compare this thing to, but I actually don't know how the inequality is going to turn, or I don't know, or I potentially could know, but it'll just take forever for me to figure it out. I just don't want to go through it. So that's kind of in the situation where I would say, okay, consider the limit comparison test in this case. So I would tend to favor the direct comparison unless it's really annoying or impossible to actually assign the inequality in the right way. But these would be the things I would think about, right? So I see this and I would know I can't integrate that because I know all the techniques and I know when they would be useful and none of those things are fulfilled for this integral. So I know I'm not going to integrate this directly. So I know I need to use some sort of comparison. The obvious thing is now I need to find what I need to compare it to. For an expression like this, comparing it to the largest powers and ignoring everyone else makes a lot of sense. I got that intuition from doing limits in Calc 1. But now the question is, how do I know who's larger or smaller? So I can use the comparison theorem. And it turns out it's not exactly obvious here. So that's when I think, okay, maybe limit comparison theorem can work. And so I would say something like set f of x equals, doesn't matter, the original was x plus 10. So yeah, it was x to the fifth plus 2x plus 1. And my g of x equals the 1 over x squared. Then the limit of f divided by g is going to be this divided by 1 over x squared. You keep, change, flip. We don't know that rule. And we are taking the limit that's really just the limit of x to the fifth plus x cubed plus 10x squared over x to the fifth plus 2x plus 1. And we know that this leads to the limit is the ratio of the leading coefficients, again from Calc 1. So that gives us 1, which is greater than 0. So this means our original integral converges by the limit comparison test. Theorem. Since we know that 1 to infinity of 1 over x squared converges. So that would be this problem there. So this stuff was just me like thinking through the problem, like how are we gonna, what do we compare it to? How would we compare it? And so something like that would go through my head. So I'm seeing this guy. I would think about, obviously I'm going to use comparison. What do I compare it to? Looking at the larger powers makes sense, but how do they actually relate to each other in inequality? I don't know. So I'm thinking I'm going to use limit comparison. So set my f and g that way, take their ratio, take the limit, I get a positive real number. So the limit comparison test will tell me that they both do the same thing. They'll either both converge or they both diverge. And I know that one converges because I have that theorem. Integral from 1 to infinity of 1 over x to the p dx converges as long as our p is greater than 1. So obviously in the case of 1 over x squared, p equals 2, which is greater than 1, so it converges. And so I know that this one converges as well. So that leads us to the correct conclusion here. So any questions before we take a break? All right, so we'll take a break, take 5 minutes, and then we will return. See you guys soon. Okay, so we're back, and that ends everything we wanted to do on improper integrals. So let's actually move on to the next and last section that we need for the test, which is numerical integration, aka approximate integration. And it's actually a very short topic, but I actually do want to go into some exposition. In the end of the day, what you're going to need to know are these formulas, and you're going to apply them. There's actually very little calculus in it. It's like an algebra problem, but you're just using these formulas. But I do want to talk about it a little bit, and so that's what we shall do. Is everything okay? All right. So here I'll focus mostly on there are two new rules, the so-called Trapezoid Rule and another rule called Simpsons Rule. But there are actually more rules that you're expected to know, but you actually saw some of these back in Calc 1, so there's really no need for me to go over them. But you're also expected to be able to use, there was like a right-hand rule, left-hand rule, not from physics, from Calc, and midpoint rule. There's some sort of event going on also. Someone's name. And midpoint rule. Okay. So the idea is the following, right? So we learned all sorts of techniques to do all sorts of integral. That was like most of the time we spent so far. We've also learned that there are times when our definite integral doesn't behave, right? So there's something off about it, that because of that, we can't use the fundamental theorem of calculus to compute our integral, so that the function is discontinuous or the limits are infinite. And such integrals, we call them improper integrals, and we know how to deal with those, right? Now, there is another case that we have to worry about. It turns out sometimes you have just regular innocent looking integrals that they're not improper, but at the same time, we can't compute them, right? So they're literally impossible to do. So for example, the integral of sine of x squared, for example, that has no antiderivative, or the integral of e to the minus x squared, that has no antiderivative. The integral of e to the x squared has no antiderivative. It means that I can do these functions here, for example. These are obviously continuous functions, and the limits are finite. So there's nothing wrong with this function. The limits aren't infinite, and the functions are continuous. Technically, we should be able to apply the fundamental theorem of calculus here. However, for the fundamental theorem of calculus to be used, you need to be able to find an antiderivative. And it turns out these functions do not have antiderivatives in any traditional sense that we're used to. So all the functions that you've learned so far, there is no way to actually think about what function would I have to differentiate in order to get e to the minus x squared, right? There's no combination at this point, no finite combination of trig functions, exponential functions, log functions, inverse trig functions, polynomials, rational functions, radical functions. Any combination of that you can come up with, you will not find a function that when you differentiate it, e to the minus x squared is going to be the answer. So these functions have no antiderivatives in terms of elementary functions. So that kind of throws a wrench into the problem. So there might be integrals that we'd actually want to be able to compute And it's very difficult or impossible to actually deal with them analytically or by hand or by directly, and for example, this integral would be very useful in, say, a statistics or probability context, for example. So now the question is, well, if we can't actually calculate the integral, the next best thing is to approximate them. And so if we can't get the answer, we should at least want to get close to the answer. And conceptually, this is something that a lot of students find uncomfortable. If I want to say it that way. Now, the way I said uncomfortable probably makes you uncomfortable. Okay, so a lot of students have this idea, it was drilled into them from they were young, like, every problem has an answer. There's always one answer. You always have to get it correct, or there's only one answer in math. Blah blah blah. A lot of people have this idea, and the truth is, like, there's so many things in math for which we don't know the actual answer. Like, we can't even get to it. We can't get our hands on it. The best we have is approximation. And so a huge area of math is about knowing how to approximate things well, knowing how to get close to the answer and not having the exact answer. And on one hand, you might think this is actually a cop-out. Like, man, we're doing problems where we can never actually get the answer. We can only get close. Like, what is that? And until you sort of realize that math is sort of an idealized world, there are times when even if we have the exact right answer, we couldn't use it anyway. Like, if I wanted to, like, okay, I did the calculations and I know to construct this building, I need this column here to be exactly pi meters long. Okay, go make a column that's exactly pi meters long. You cannot do it in reality, right? Every instance of pi in reality is an approximation of pi. Like, your computer doesn't know what pi is because there's an infinite amount of non-repeating decimals. No computer on the planet can actually store all the digits of pi. Every time you do a calculation in a computer, or you're cutting something with a machine, or you're measuring something in reality, and it's supposed to be some irrational real number, it can't be done. It literally can't be done. We cannot do this in reality. So even if I knew the answer was pi, okay, I have the satisfaction of knowing the answer was pi, but it's not worth any more than that. Because if I'm going to build something in the real world, I cannot make it pi units length. I cannot measure out pi pounds of something. It's not something that can be done. I can only be as accurate as my scale is going to be accurate. And my scale is going to be accurate to a rational number. It's going to be accurate to a certain amount of decimal places, and that's it. So not only is, like, approximation a big thing that we can do and sometimes we can't escape, but sometimes it's the best we need. We don't need to go beyond that. So we need to know how to deal with approximations, right? Because sometimes they're actually the gold standard, and knowing the actual answer a lot of the times gives you nothing other than, oh, you can pat yourself on the back. So now we come to integrals. We want to be able to calculate integrals for various reasons, various applications, but we can't do it exactly. So the next thing we want to do is approximate them. And this is not a cop-out. This is actually big boy stuff. We're going to be adults about this, and, like, no, actually, practically, it's okay that we don't have the exact answer or the exact right answer. It's okay to be wrong a little bit, because even if we had the right answer, we couldn't do anything with it. So that's what we're going to do. Now, when it comes to actually approximating integrals, definite integrals, you can go back to first principles and kind of remember where the integral came from in the first place. The integral was the limit of things called Riemann sums, right? This was one conception of the integral, right, by Riemann, which is about 100 years old, a little more than 100 years old at this point. I think Riemann wrote his PhD thesis about this new way to integrate in 1905 or something like that. So it's a little bit about over 100 years old. So the idea was the integral was basically trying to find the area under a curve. That was the whole point, figuring out how much space something takes up. And the idea was because we had this weird, we can have weird shapes where we don't know how to compute their area, we can use things to approximate the area with shapes that we know how to find their area. So instead of finding the area under this curve, which might look like that, and I don't know, and I want to find the area between under this curve between A and B, like I don't have a formula for that, but the idea is I know how to find the area of a rectangle. And so I can put up a bunch of rectangles under this curve to kind of approximate it. And so we had something called the left-hand rule, where the left side of the intervals. So what we would do is we would break this up into subintervals, you know, like an x1, an x2, x3, this would be like your x4, this would be like your x0. And then on each of these subintervals, we erect rectangles. And there are all sorts of rules that we can talk about for how we construct these rectangles. So one is the left-hand rule, which tells us that the left side, we let the left side of the integral go up, hit the curve, and then we cut off the height of the rectangle at that point. So the left side comes up, hits the curve. That is the height of our first rectangle. Then I look at the next subinterval, the left side comes up, hits the curve. That is the height of the second rectangle. Then the next subinterval, x2 to x3, the left side goes up, hits the curve. That is the height of the third rectangle. Then for the interval x3 to x4, left side goes up, hits the curve. That is the height of that rectangle. And then we kind of use the areas of these rectangles as an approximation for the area under the curve. Now in this scenario, obviously, the areas of the sum of the areas of the rectangles will be a little bit bigger than the area under the curve. This is an overestimate, we call it, right? Where we get something that's larger than what the actual answer is, but it actually helps us. Now, we actually break this up in a systematic way. So for us, we always break up the interval into an equal lengths. Each of these lengths is what we call delta x. And we actually have a formula for delta x. Delta x equals b minus a over n, where n is the number of subintervals. Right? So this takes the length AB, which is going to be b minus a, and we slice it up into n parts. In this case, n equals 4. So I slice this up into 4 subintervals. And then from that, we can say that the area is going to be approximated by me adding up the sums of the areas of this rectangle. So I'm going to sum from I goes from 0 up to 3, because only the x0, the x1, the x2, and the x3 take effect here, of the height of this rectangle, f of xi, times delta x, which is the width of these rectangles. And that I can actually use to approximate the curve. More generally, I can go not up to 3, but we can think of this as going up to n minus 1. So in this case here, this is our f of x. And I'm choosing n equals 4, right? And so that was a way in which I could actually approximate the area under this rectangle. Now, let's move this over a little bit. Now, another option I had was to give myself more space, right? And this was like me using the left-hand rule, which basically just tells me, oh, I choose the rectangles based on the left side. Okay. Another option I could have done was using a midpoint. So again, I have this function. I want to find the area under this curve between A and B. I don't have a formula for it. So I broke it up into subintervals. x0, x1, x2, x3. And so these are some subintervals. And then the midpoint rule tells us that what we do is we choose the middle of the interval to determine the height. So I would go in here, and I'll go in the exact middle of this interval. That determines the height of my rectangle. Middle of this interval, that determines the height of my rectangle. That determines the height. That determines the height. These guys I call x1 star, usually x2 star, x3 star, x4 star, which are just the average of the two outer integrals, right? So now my rectangles will be this height, and then this height, and then this height, and then this height. Now here, in this case, you see me kind of trying to correct for the over approximation here by actually, I over approximate on one side and under approximate on the other side. In this scenario, that's how the midpoint rule ends up looking. So here I would get that, oh, I can use my area to be, you know, it's a sum. I goes from 1 up to n, or 4, of f of xi, which is going to be the height of each rectangle, times delta x. And here it's where your xi is just the average. So it's going to be x I plus xi minus 1 all over 2. Just take the average and it'll get you the middle values. Another option was to use what we call the right-hand rule. So we have our function here. This is our y equals f of x. And again, our n equals 4. I'm going to use, for example, y equals f of x, n equals 4. So again, I want to find the area under this a to b. I can cut this up to some amount of rectangles and subintervals. And for the right-hand rule, I use the right side of each subinterval. So this is, here is x0, this is x1, this is x2, this is x3, this is x4. I can use the right side, determines the height. So then I would have a bunch of rectangles like so. Then I can find these areas. Now, clearly this one is an underestimate because all my rectangles are under the curve. So the area I get from adding up these rectangles will not actually give me the area under the curve, but it will give me something slightly smaller. And so here I can say my area is going to be me summing up. I goes from 1 up to n instead of from 0 up to n minus 1, because here I'm looking at the right side of f of xi times delta x. So this is like the height and width of the rectangles, right? So this is the height. This is the width, right? And I can actually do that. So this actually gave us some formulas, and these guys could be written out as something like, you know, it would be delta x times f of x1 plus f of x2 plus f of x3 plus f of x4. Right? Now, so far, everything I've said at this point, you should have seen in Calc 1. Essentially, we're taking the same idea, right? So in Calc 1, you would have had a problem. Oh, approximate the area under this curve using n equals 4 subintervals and right-hand rule, right? And then all you know is that you'll just do this, right? Compute delta x, which is always going to be b minus a over n. Then you're going to find all the right sides of the x values, and you're going to plug them into your function. Plug in this number, plug in that number, plug in that number, plug in that number, add them all together, multiply by delta x. That gives you an approximation of the area. And of course, the idea is the more rectangles you use, the better your approximation gets. And the idea, of course, is use enough rectangles so that your answer gets close enough to what the actual answer is that you would want. Generally speaking, I mean, for a lot of these problems, we could get the exact answer. And in Calc 1, you would usually have a problem where they ask you to approximate it, but then actually find the actual answer. In real life, that's not always possible to find the actual answer. But there's going to be a way for you to approximate it and get as good an approximation as possible. And so in this chapter, what I'm going to do is I'm going to teach you 2 additional ways of approximating errors under the curve. So I do expect you to remember these ways that you did in Calc 1, which is why I went and reviewed them. But now I'm going to teach you 2 additional ways, and I want to talk about those. So now, a question that you are often also asked is whether there's an overestimate or an underestimate, right? So for example, here, I can tell you that ln, this was like the left-hand rule with n subintervals. This was an overestimate. And the mn, this here was an underestimate, I think. Because there's a concavity rule, but it's not obvious in many cases. And our right-hand rule was an underestimate. And you can actually just see these directly from the picture. Right, the midpoint is kind of hard because you overestimate some places, underestimate other places. But there's actually a theorem about concavity that says it would be concave up, it would be underestimate. But if your function starts doing this, then it becomes a lot harder to actually judge that. And I guess that's true for all 3 of them. Like if your function is too uppy downy, too jagged, it's going to be kind of hard to determine whether they're overestimates or underestimates. But for some simple examples, you can actually determine those questions. And because this topic is generally just kind of a plug-in to a formula and it's not very difficult, sometimes you might ask conceptual questions like, tell us if it's an overestimate or an underestimate. And that might be something that you want to do. So in the above, this was true. And this was left-hand approximation. With n subintervals. And this was the midpoint approximation. And this was the right-hand approximation. Okay. So now, let's actually talk about 2 other rules. So we're going to do something called the Trapezoid Rule, where the idea is you use trapezoids and not rectangles. So for that, you should remember what the area of a trapezoid is. So trapezoid has 2 parallel lines and 2 parallel sides, and then the other sides might not be parallel. But what you can do is you can find the area of this by just taking half the sum of the length of the 2 parallel lines times the distance between them. This is just going to be the formula for the area of a trapezoid. So I'm not going to derive that for you. I'm just going to tell you that that's what we're doing here. That's how we're going to look at this. So in this case, what we're going to do is we have our function here, and the idea is between A and B, let's say we have 4 subintervals again, then a half, and cut that in half. What we want to do is instead of using rectangles, we would use trapezoids. And so the idea is here, we will use these endpoints of where the intervals actually touch the function, and we'll connect them with a straight line. So like this red, and this, and this, and this, and then add the vertical sides. And you notice that all these red thingies are trapezoids. They're not rectangles anymore because they have a slant edge. And again, the idea is to get closer to the answer with less intervals than this, because the thing with the flat top here was very clunky. It was easy to get an over or underestimate. So the idea is if we use trapezoids, it will slant more with the curve and give us a better answer. And not that it would give us exactly the right answer either, but it will get us closer with the same number of rectangles on average, right? So this is the idea. Okay. And so now we want to actually figure out, well, how do we actually go about getting a formula for this one? Because it's not as straightforward as, oh, height times width. It's the half the sum of the two parallel sides times the distance between them. And so if you actually figure out what that would actually look like here, so let's say this is x0, this is x1, x2, x3, x4, and I wanted to say find the area of like this one, area, right? Now remember, the distance between these is delta x, and it's going to be delta x for all of them. Okay, so now if I go along with this formula, this is going to be 1/2 the sum of the two parallel sides, which will be given by f evaluated that value, that gives you the height. So this part here would be f of x0 plus f of x1 times the distance between them. This one, the area is going to be very similar, 1/2. This will be f of x1 plus f of x2 times the distance between them, and so on and so forth. And so what you do is you will now add up all these formulas. So ultimately you would get the following, right? So, and this you can kind of think of as, you know, delta x over 2 times f of x0 plus f of x1. This you think of as delta x over 2 times f of x1 plus f of x0, f of x2. Etc. Right? And so now when you stick these trapezoids together, you can find the total area, right? Prox for total area. And so you would get, oh, maybe I should write this as T sub 4. So that's the trapezoid approximation with 4 subintervals. So our actual area, we can approximate with just the sum of these formulas. So that would look something like, you know, delta x over 2 times, hold on, give me a second. Yeah, the cat was running amok. Okay, all right. So these formulas would look something like, I'm just adding up these guys. So here I would have f of x0 plus f of x1 plus delta x over 2, f of x1 plus f of x2 plus delta x over 2, f of x2 plus f of x3 plus delta x over 2, f of x3 plus f of x4. and would actually end there. What you'll notice then is that some of these guys actually pair up. Like there are two of these. And there are two of these. And there are two of these. So notice that there are going to be two of everybody except the first and the last guy. And so if you wanted to like factor out and compress this a little bit, this will actually be delta x over 2. And then I'm going to have f of x0 plus 2 f of x1s plus 2 f of x2s plus 2 f of x3s, and then just an f of x4. So if I wanted to do a trapezoid rule approximation for this guy, that would be the approximation. So that would be the formula. So it's not just like a delta x times f of blah, f of blah, f of blah. Here, it's a delta x over 2 times f of the first guy, f of the last guy, plus 2 times f of all the other in between guys, right? So that leads us to this formula for the trapezoid rule formula, right? And so that is just how we do the trapezoid rule. So at the end of the day, if I ask you to apply a trapezoid rule approximation for something, this is how you would actually do it. So it's just going to be like Calc 1 when you're doing left-hand, right-hand midpoint, except the formula is actually different here. It's delta x over 2 times all this stuff. So the first one and the last one are just you take f of x. And then for all the intermediate subintervals, it's 2 times f of that point, 2 times of this point, 2 times of that point. And this leads us to the trapezoid rule. And in some cases, this will give us a nicer answer. It will get us closer to the answer than like the midpoint left hand or right hand with less rectangles. And so that's the idea. We kind of want to know when we want to do that. And here again, your delta x is the same, b minus a over n. That's always going to be true. So that is how we get the trapezoid rule. Now, I want to talk about the Simpsons rule formula. For that, we need to know how to find the area under a parabola. Because Simpson, the idea there is, okay, we've seen it using rectangles and we've now seen it using trapezoids. But again, things are wavy and curvy, and so kind of using a straight line thing kind of makes you feel like you're always just going to miss too much. And so one thing you could actually do is start to get something curvy to kind of try to fit the curvy lines. And so Simpson actually uses parabolas. So you might be in a situation like this where, you know, this is your wavy thingy, this is your A, this is your B. So how Simpsons works is, you know, let's see, here, here, here. You have to, by the way, you have to split it up into an even number of intervals. So that's the first thing, and I'll mention that why that is. So each interval, you kind of think of it as a pair of intervals. And the reason is because you want to construct not a rectangle, not a trapezoid, but an actual quadratic function. And to uniquely determine a quadratic function, because you have ax squared plus bx plus c, you need at least 3 points of contact. So you have 1 point of contact, 2 points of contact, 3 points of contact. For this, you need each subinterval to have like 2 halves. So you'll always have an even number of subintervals, right? So this is going to be like your x1, your x2, x0, x3, so on. But now what we can do is we can construct a parabola that passes through that. And then you do the same thing here. Like so you have this point, that point, and then you construct a parabola that passes through that. And then you go over here, then you have this point, this point, this point. You construct a parabola passing through that. And then over here, split that interval in 2, you get this point, and that point. Then you construct a parabola passing through that. And then what you do is on each interval, you find the area under that parabola that you constructed for that interval. Right? And so this gives you what's called the Simpsons approximation. And when you have quadratic, because you can actually do this for cubics and higher, but the one we're going to cover only does it for quadratics. This is called Simpsons 1/3 rule. So this is the one that we're going to be looking at. Simpsons 1/3 rule. So obviously for doing this, we need to know how to find the area under a quadratic, which isn't hard, but to put it in a nice formula, we're going to actually do something a little bit, we're going to have to use special notation and things like that so that we don't get lost. We kind of know what we are doing. So here, you know, our parabola is, let the parabola be, you know, p of x equals ax squared plus bx plus c. Okay. And so let's imagine that there is an interval here that we care about to here. So I'm going to call this, say, x0, call this x2, and the middle one, which I want to line up with the axis, is called x1. And then I have some parabola over here, and I actually care about finding, so these are my subintervals. I care about finding the area under here. So we want the area. So obviously this is going to hit a coordinate. This is going to hit a coordinate. This is going to hit a coordinate. So let's call this x0 comma y0. Let's call this x1 comma y1. Call this x2 comma y2. Now, the idea is if we can figure it out on this balanced interval, we can figure it out anywhere, because then it's just a matter of translating wherever the parabola shows up. So if we can find a general formula where the parabola is like mid-centered on the axes. So this is at, say, we usually call this minus h to h, but for us here, h is like literally delta x, right? But we're going to use just some shorthand notation. So we can actually do the calculation for the area under this curve. So the area under this curve is going to actually be, integrate from minus h to h of our ax squared plus bx plus c dx. Okay. So we actually know that the integral of an odd function on a balanced interval is actually 0. So we know we don't have to calculate that. This is something we know from Calc 1. So otherwise, we're going to go in, this will be ax cubed over 3 plus cx between minus h and h. And then if I actually plug those in, I would get ah cubed over 3 plus ch. If I'm putting a negative h and a minus, this will become plus ah cubed over 3, then a minus. So this also becomes a plus ch. So this gives me actually 2ah cubed over 3 plus 2ch. We can factor out an h over 3. And then I would have 2ah squared plus factor 8. So this 6c, because then it's 6 divided by 3. Okay. So we have that. And if we take a look at the following. So here's one thing that we know from the picture. I actually know what the parabola evaluated at 0 is going to be. Right? That's actually just going to be our y1. Which of course is C here. Because this is also my parabola. So if I plug in x equals 0, I just get C. So my C is actually equal to y1. I also know that the parabola at minus h, that's going to be y0. But y0 is also AH squared plus minus h, so it's minus BH plus C. And then I also know that at h, this is actually equal to y2 according to my diagram. But if I plug in positive h into the parabola, I get AH squared plus BH plus C. Now, if I take these two guys and I add them, I get that y0 plus y2 is actually going to be equal to 2AH squared plus 2C. So here, I can go in and I have 2AH squared plus 2C, and I separate this 6C into 2C and 4C. So now this one, this here can be replaced by this. So I'm going to take this and replace it by that expression. So this is going to be y0 plus y2. And I can take the fact that C is y1. And so this one here, I'm going to actually be able to replace that with 4y1. And so this is going to be h over 3 times y0 plus 4y1 plus y2. Now, if I sort of go back to the notation we've been using, our h is like our delta x, so you get delta x over 3. y0 would be like f of x0. y1 would be like f of x1. y2 would be like f of x2. So then if you go and you start adding all these guys together, you would get something like, if your area is approximated by Simpsons rule with, let's just say we were using 6 subintervals. So it's like I have this kind of guy here, like where each of these guys here has a parabola. One, two, three, four. 1, 2, 3, 4, 5, 6. Right, so this is like your y0, y1, x0. It's like your x0, x1, x2, x3, x4, x5, x6. So for each of these, I would have like a delta x over 3. So for the first one, I would have something like y0 plus 4y1 plus y2. Then for the second set, that would start at y2. I would have y2 plus 4y3 plus y3. Then for the third set, y4. For the third set, I'd have delta x over 3, y4 plus 4y5 plus y6. In other words, I can shorthand write this as delta x over 3. My y0 would just be f of x0. Now you have something interesting because these two here match up. So they're two y2s. They're also two y4s. But everyone else kind of, the guys in the middle don't match up to anywhere else. So we would have 4 times f of x1 plus 2 times f of x2 plus 4 times f of x3 plus 2 times f of x4 plus 4 times f of x5 plus f of x6. So you have this alternating pattern going on here. 4, then 2, then 4, then 2, then 4. It turns out it'll all, after the first one, which has no coefficient, you'll start with a 4 and then you'll alternate between 4 and 2. You'll end with a 4 just before the last one, which has no coefficient other than 1. And so you have this 4, 2, 4, 2, 4, 2 pattern. And that just comes from actually calculating the area under this parabola. And so that leads you to Simpsons rule. So if you look in your textbook, that's what you would see for the formula there. And again, your delta x is b minus a over n. And also notice that your n must be even, because to construct a single parabola, you need like 2 subintervals connected together to get those 3 endpoints to be able to construct the parabola. And so you see this formula with the 4, 2, 4, 2, 4, 2 repeating. So again, nothing on the first or last, no coefficients other than 1. But the ones in the middle, they have this pattern that's not just, you know, the y values. It's 4 times the y value, then 2, then 4, then 2, then 4. It flips between 2 and 4. It'll end on 4 on the second to last one. And then that will be the formula. So these are the 2 new formulas. So these will be added to the ones you know from Calc 1, which are these, which you could write out like this. But now you have some more sophisticated formulas. Right? And this is specifically Simpsons 1/3 rule. Because there are others, right? You can actually do constructions with cubics and quadratics and things like cubics and quartics and higher, but the one with quadratic is called Simpsons 1/3 rule. And that's because, you know, 3 subintervals, the 3 endpoints on the interval. So that's that. Now, at some point, because you're doing an approximation, it's not just you do an approximation and you're good. You would always want to know how good the approximation is. And so there are some formulas that we can use to figure out the error term for one of these approximations. In other words, it tells us how far off from the real answer we would be if we use one of these approximations. So there are some formulas here that kind of give you a worst case scenario, like this is the worst off you can actually be by using one of these rules. So E sub m is for the midpoint rule. And so you can actually do a calculation to tell you, when I use the midpoint rule, how far away from the actual answer could I possibly be? You can do this for the trapezoid rule, and you can do this for Simpsons rule. And in the above, k is a constant such that this is true. And generally, you can pick any constant you want, but of course, you want this to be the smallest such constant that this is true. And for the Simpsons rule, you actually need this to be true. Pick up a constant for which that is true, but you pick the smallest such constant you can possibly think of. And then these error bounds will actually tell you how good your approximation is. Now, you're not going to need to remember those, but I do want you to remember these. So I'm not really going to test you on error bounds in the summer or tell me how good the approximation is. It's just straight plug and chug, know this formula, plug in the values into it, and give me the approximation. And I might ask you about, well, is it an overestimate or an underestimate? Things of that sort. It's going to be sort of like a Calc 1 problem, except now you have two new formulas to do it with. So I could ask you to use Midpoint Rule or Simpsons Rule or Trapezoid Rule to do it. And yeah, that's kind of essentially it, actually. So nothing else to say other than that. And you don't need to know how to derive these things. I just, I don't really like giving you some random formula and not really talking about it. So I kind of want to show you where these formulas came from. Why is there a bunch of 2's in the middle? Why is for this one, is there a 4-2-4-2 pattern? So now you know. But for actually what I would want you to be able to do, here is an example of something that I would expect you to be able to do by hand. Right? Now, this you could actually do by hand, right? You can integrate the sine function and plug in and apply the fundamental theorem of calculus. But I just actually want to use this as an example, let's say. So let's say I wanted to use the, we're going to skip midpoint rule because it's like a Calc 1 thing. We're going to do trapezoid and Simpsons rule. And so, yeah, let's actually look at how to do that. Okay. So now, just like in Calc 1, the first thing you're going to want to do is find your delta x. So B, we're going to do trapezoid rule. So first thing you want to do is find delta x. And your delta x is always b minus a over n. So here, obviously, your interval, this tells you your interval AB is 0 to pi. And your sine function, your f, is sine of x. And here, I think we told you 4. So this 4 tells us the number of subintervals. This means your n equals 4. Right, so you can either say using 4 trapezoids or 4 subintervals or, something like that. It will tell you how many you want to use. So this means you have an x0 up to an x4 on the diagram. And so b minus a over n just comes down to actually you doing that calculation. So it's pi minus 0 over 4. So pi over 4. Right? So that's the first thing. You want to find your delta x. The next thing you're going to want to do, you have to find all these x values that you want to plug in, right? You know the x0 is your a. You know the xn is your b. What is the x1, the x2, the x3, the x4? Like you need to know those. So you also go in and you find the xi. Now I sort of like to draw a picture here. So this is 0 and this is pi. And of course, this is going to be your x1. And this is going to be your x4, which is like your xn. And so 4 subintervals means you split this in 2 and then split each of those in 2. So here you're going to have your x1, here you're going to have your x2, here you're going to have your x3. Now, what are those? One thing we do know is the distance between this and that should be delta x. Same thing here, delta x. Same thing here, delta x. Same thing here, delta x. In other words, you add delta x from one point to get to the other point. So here my delta x is pi over 4. I'm just going to add pi over 4. So this is going to be equal to pi over 4. Because I start from 0, add pi over 4. Then I take pi over 4, add pi over 4 again. That's going to give me pi over 2. Take pi over 2, add pi over 4 again. That's going to give me 3 pi over 4. Add 3 pi over 4, add pi over 4. That ends up with pi. So I'll actually get the last one. So I start with 0, and I keep adding delta x until I get to the last one. This is going to fill in all the lower x's for me. Now, once you do that, here's where you're going to plug into the formula. So now we know for the trapezoid rule, it has that pattern where all the inside y values, you're multiplying them by 2 when you add them up. The first and the last one, you don't do anything, and you multiply by delta x over 2 on the outside. So here we know that this area, we're approximating it by trapezoid rule with 4 subintervals, and that is going to give us delta x over 2 times f of x0 plus 2 f of x1 plus 2 f of x2 plus 2 f of x3 plus f of x4. And that's now what we're going to do is we're just going to plug in numbers here and do the calculations. So now our f is just the sine function, right? So I can write this out a little bit. So this is going to be pi over 4 divided by 2. And this is going to be f of 0 plus 2f of pi over 4 plus 2f of pi over 2 plus 2f at 3 pi over 4 plus f at pi. So this is actually pi over 8. What is our f? This is sine. So it's sine of 0 plus 2 sine pi over 4 plus 2 sine pi over 2 plus 2 sine 3 pi over 4 plus sine pi. And I do expect you to know what these values are. So sine of pi is 0. Sine of 0 is 0. Sine of pi is also 0. Sine of pi over 4 is rad 2 over 2. I'll just write this in a line. Let's write this in another line. So sine of 0 is 0. Sine of pi over 4 is rad 2 over 2. Sine of pi over 2 is 1. Sine of 3 pi over 4 is also rad 2 over 2. All students take. So positive, and the reference angle is pi over 4. And then sine of pi is 0. So this cancels, this cancels. So I get pi over 8. And I have 2 plus 2 rad 2, which is like pi over 4 times 1 plus rad 2. That would be your answer. That's your approximate area. Right? So at the end of the day, if I ask you to approximate something using 4 subintervals and trapezoid rule, you're going to find your delta x, which is always b minus a over n. You're going to find all the other xi. Just draw your intervals, cut it up into as many subintervals as you want. Start with the x0, add delta x as many times as you need to get to the last point. And so that finds all the intermediate x values for you. Then you plug into the right formula. So in this case, it's the trapezoid rule formula. And you simplify, and you can get an expression for the approximate area with the trapezoid rule. So now we are going to do to approximate 0 to pi sine x by Simpsons rule. with n equals 4 when we return. So we're going to take another break. Maybe you can even think about doing this. This might be something that you can do during the break. It shouldn't take you too long, but otherwise you can take a break and take a 5-minute break, and we'll come back and we'll do that. And this will actually end this section after we do this example. We'll start talking about something else. So see you soon. Okay, got the thumbs up. All right. So I think got more than 5 minutes. Like I had in my head, I think I had in my head that we stopped at 8:10, but and now I'm thinking about it, I think it was probably 8:05. Maybe 8:10 is when I wanted to come back. Either way, you got a longer break probably than we should have. So let's actually continue. Want to do the Simpsons rule. And there's like some sort of jazz concert or something going on outdoors. I don't know what's going on, but yeah, let's see here. We are going to start something. Okay. Let's actually finish this and then we will figure out the rest. Okay, so again, when you want to do this, actually, okay, here's an integral I want you to approximate it using Simpsons rule with n equals 4 subintervals. Or I say trapezoid rule. The only difference between those two things is the formula that you use at the last step. But the first step is, find delta x. Delta x is always going to be b minus a over n, where a is the lower limit, the left endpoint of the entire interval that you care about. B is the upper limit, the right endpoint of the entire limit interval that you care about. So in this case, it's pi minus 0 over 4, pi over 4. Then 2, you're going to find the other xi. So I like to visualize it by drawing this interval. So this is going to be 0, which is your x0. It's going to be pi, which is your x4. In this case, our xn. Then I'm going to have 4 subintervals here. So this is going to be my x1, x2, x3. And then what I do is I add delta x. So this guy gives me pi over 4, add delta x. This would give me pi over 2, add delta x. This will give me 3 pi over 4, and add delta x. And that would give me pi, which is also another check that all my other guys are right, because on the last step, if I add delta x and I don't get pi, that would actually mean I messed up somewhere. So that's gonna break it off. And 4 intervals is usually decent for me to ask about. Maybe 5 if it's a trapezoid rule problem. For the Simpsons rule, it always has to be an even number. 4 is a pretty nice number. So you'd have to do this for 4 or 5 intervals. I don't really see any pedagogical benefit to going beyond that. Like if you can do it for 4, you can do it for 6. There's no reason to actually go too far. But yeah, here, those are the xi. So the last thing you want to do now is you can actually plug into the formula. So for Simpsons rule, it would be our error is going to be approximated by s sub 4. That's given by delta x over 3 f of x0 plus 4 f of x1 plus 2 f of x2 plus 4 f of x3 plus f of x4. So remember, first one is just f of x0. Then you start alternating with 4, 2, 4, 2, 4, 2. The middle would start and end on the 4, but alternate between 4 and 2 in the middle. And then for the last one, the f of xn is just f of xn. And so in this case here, this would be delta x over 3. This is going to be pi over 4 over 3. And this would be f of 0. 4 times f of pi over 4. 2 times f of pi over 2. 4 times f of 3 pi over 4. And f of pi. So this comes pi over 12. This is sine of 0 plus 4 times sine pi over 4 plus 2 times sine pi over 2 plus 4 times sine 3 pi over 4 plus sine of pi. So now we plug these in. Sine of 0 is 0. Sine of pi over 4 is rad 2 over 2. Sine of pi over 2 is 1. Sine of 3 pi over 4 is rad 2 over 2. Sine of pi is 0. So this gives me pi over 12 times 2 rad 2 plus 2 plus 2 rad 2. So that's 4. That's 4 rad 2. Let's put the 2 in front. 2 plus 4 rad 2. In other words, you can write this as pi over 6 times 1 plus 2 rad 2. That would be the approximation. Okay, any questions on that? You're good? Yeah, so that's pretty much it. That's all the stuff you need for the test this week. So remember, practice tests will be on Gradescope. There's already one up that's untimed, but I will post a few more that are timed and also more comprehensive, I guess. And right now, I did prep some notes for the next thing I want to talk about. So we're actually going to talk about actually get okay, that's a little off center. I don't want to waste time fixing it now. All right. So we're on to phase 2 of the course. All right, so we just finished phase 1. So we had like a phase 0 where we talk about inverse trig functions and hyperbolic trig functions and some other things that we wanted to know in the background. Then we did phase 1, which was just me teaching about integration techniques, right, which is a big chunk of the class. The next big chunk of the class is sequences and series, mostly series. And after that, we'll have like a phase 3 or whatever, where I clean up and do some more applications of integrals, and we can do things like arc length and talk about polar coordinates and things of that sort. But right now we're going to talk about sequences and series, and we're starting a new topic from scratch. So what I'm going to be talking about is more like definition stuff, concept stuff, like introduce all these new ideas. We're not really going to do anything too crazy today, but there are some important ideas we want to understand. Let's quite line up anyway, whatever. Okay, so we're actually jumping to chapter 11. So we're going to talk about sequences. Now, like I said, the bulk of what we want to talk about is actually series, but you can't really talk about series without first knowing about sequences. So that's what we are going to talk about. So for one definition, I'm going to give you a few definitions of series sequences. I'm gonna mess that up all the time. I'm gonna give you a few definitions of sequences, and then we're gonna interpret all of them and show you what they mean. But for now, what you can think of a sequence as is just a list of numbers in a definite order. Okay, so that's not really generally what a sequence is. It doesn't have to be numbers, but for us, this is what a sequence is. You have a list of numbers and there's a definite order. There is some sort of rule in the background or algorithm or process that I'm thinking of that causes these numbers to come into being. I'm thinking of a rule and I can write down a list of numbers that go according to this rule. If I can do that, you can say I'm writing out a sequence. Okay, so examples of sequences. So for example, here, I write down a list of numbers, -1, 3, 7, 11. This is a sequence. And in fact, because this list ends, it's called a finite sequence, right? So this is a sequence with 4 terms, right? So each element in the list is called the terms of the sequence. Okay, so now there's such a thing as finite sequence. There's a finite list of terms. And on top of that, I would say this is not the focus. Okay. But there is something that's called an infinite sequence, which means it can be an infinite list of terms. So I can have an infinite list of numbers that I'm writing down. And in my mind, there's some sort of rule or algorithm that I'm going through to write down the numbers in this list. But that rule never stops. It just keeps going and keeps giving me numbers that I can write down. And so I can have what's called an infinite sequence. And we'll focus on these. Okay. Now, ellipses, of course, like these 3 little dots right here, that is just indicates that the pattern continues, right? So in this case, if I put ellipses at the end of a list, it means that, oh, you should assume this list goes on forever. If I just put a period or I don't put anything, then you just assume the list stops at that point and there's nothing else to really talk about. Okay, so usually we can name sequences with lowercase letters, and this will sort of be the way that you would do it. So for example, for a finite sequence, say with k terms, let's say, I can write it to say, oh, the sequence is called an. Sorry, n goes from 1 up to k, right? And I can write down this notation, and that would mean, oh, this is a sequence described by the letter A and subscript n that goes from 1 to k. And, or I can say an infinite sequence. And then I would write that down as like n equals 1, and I'd put a little infinity here. Or for us, I can just write an in squiggly brackets, and it is understood. to be an infinite sequence. Now, occasionally, we'll start the list somewhere other than 1, like 0 and 1 are both very common things to start a sequence in. But what happens is that you can actually name the terms of your sequence based on the subscript of where they show up. So for example, in this list of 4 terms, I can call this one A1, and this A2, and this A3, and this A4. And then the whole list, this is described by AN. N goes from 1 up to 4. So I can talk about that, such a sequence, right? So the entire sequence, we call it with these curvy brackets. You can name the starting subscript and the ending subscript. These are just integers that you can use to account for what position the element is in. So if I have a sequence AN, and then I ask you about what is the third element, that is A3, A subscript 3. And so in this case, that would be the 7. And I could do that for this one as well, right? So I could call this BN. Now clearly here, N goes to infinity, but this would be B1, this would be B2, this would be B3, etc. And that just keeps going, that pattern, right? So that's how we can actually name sequences, for example. And the idea is, in our situation especially, there will be some sort of pattern or formula that we can actually describe what's going on and how we can determine the points in our sequence. And sometimes we want to be able to find this because it'll actually be very useful. So, I mean, as right now, like the first sequence, what do you think is a pattern that would give me that list of numbers? Do you notice anything? What do you think a pattern would be?
+4.
I think a part of it cut out. What were you saying?
Oh, I just said +4.
What +4?
Would it be A or X or? I don't know, you're just adding 4 to each of the numbers.
Right. So when you just say +4, it doesn't really tell me where it would start. Right? So I see someone saying odd. Well, they happen to always be odd. But if I wanted to say, if I wanted to write down a formula based on the, say, the N or the subscript, what could it be?
-1 + 4n - 4.
-1 + 4n - 4.
Yeah, or 4 times n - 1. I just expanded that
Oh,
out.
well, okay, so we could take the -1 and the -4 and combine them into -5. And
Oh yeah, right.
yeah, that would be it, right? That's one way we could describe the first list. Right? Notice what would we get here? If we use that formula, what would we have? Well, A1 would be -5 + 4 × 1, which gives us the -1. A2 would be -5 + 4 × 2, which would give us the 3. And notice that here I keep adding 4. A3 would be -5 + 4 × 3, which would give us the 7. A4 would be -5 + 4 × 4, which would give us the 11, right? And notice that each one here, I'm adding 4. But knowing that adding 4 is the rule, yes, that's exactly what you do when you say, oh, we start at -1, and then we keep adding 4, and we do that 3 times to get a list of 4 things. Well, that is true, but that's not really a formula. At some point, having a formula is actually going to be the nicer thing that you actually want to be able to do. And this is and there's going to be a standard way to actually figure that out. So if you notice something like, oh, I'm just adding this constant over and over, there's actually a standard way to write that down, right? So, and it's actually what Maxim said. It's going to be the first term A1 plus n minus 1 times the common difference, as it's called, which in this case is +4. And so this is what's called an arithmetic sequence. I'm pretty sure most of you heard of it before, but it was probably years ago, probably like way back in high school. It's like some of you are actually still in high school, so you probably heard of it recently. But there's something called, when you look at sequences, some very popular ones are the arithmetic sequence or the geometric sequence. You might see these, or they might be called the arithmetic progression or the geometric progression. This is an example of an arithmetic progression or an arithmetic series where you keep adding the same constant over and over. And usually what it's going to be that the constant times n plus some number, and that's going to be a pattern. So this wasn't just a random list of 4 numbers. There was an idea that was in the back of my mind that I was talking about, thinking about, to write down this list, and I just stopped it at a certain point. What about the second sequence? Does anyone know what the rule is or what that sequence is called? Does that look familiar to anyone?
I know it's called the Fibonacci sequence.
It's called the Fibonacci sequence. So it's actually a very important sequence, very famous, very popular, and it's super neat, super cool. Maybe at some point I'll share a YouTube video with you about it. But it's a sequence that is defined what we call recursively, and it shows up all over the place. Like there are people like, they can find Fibonacci sequences in lots of things in nature, and people are like, oh, this is a proof that God exists. It gets really crazy. Like people like fall over this sequence like they fall over pi, and oh, there's pi and everything. Okay, so Fibonacci sequence, very famous sequence, and sometimes it's called Fn. And here's the rule. So it starts by you choosing the first 2 terms, 0 and 1, and then every new term is just you adding the 2 previous terms. So to find the n plus first term, you add the nth term plus the n minus first term. So you add the previous 2. So you'll notice that that is what you would get if you look at this list. Like you start with 0, 1 as the first 2, and then add 0 and 1, you would get 1. If you add 1 and 1, you get 2. You add 1 and 2, you get 3. You add 2 and 3, you get 5. You add 3 and 5, you get 8. You add 5 and 8, you get 13. And notice that that's how we're going through this list. And it's actually very, and as an example, if you look at, for example, the average flower, for example, the number of petals on a flower will be one of these numbers, for example, right? So you'll have flowers with 3 petals and 5 petals and 8 petals, but it's very hard to find a flower with 7 petals, for example. And that's why a 4-leaf clover is it's thought of as lucky, because it's actually very strange to have something with 4 petals. And so these numbers, this list of numbers show up all over nature. You can use these to construct the golden ratio. You can use them to construct this spiral that you can see in like a sunflower and the crashing of a wave and all sorts of crap. So this is like the Fibonacci sequence, and it's a very famous sequence, but it's an example of a sequence that is infinite. And it also gives us another way of defining a sequence. So sometimes you can't really come up with a nice formula, even though in the case of the Fibonacci sequence, you can, but sometimes you can define a sequence or a list of numbers by saying the rule is to use some previous terms to construct the new terms by some rule. So I start out with 2 numbers, and every new number comes from me adding the previous 2 numbers. When you do that, and the first 2 numbers are 0 and 1, you have what you call a Fibonacci sequence. A very famous sequence, right? So you can actually do that, right? Now, another way you can think of sequences is as functions. So you can think of the input as being the subscript, or just the set of positive integers or non-negative integers, for example, and the actual numbers in the list as their outputs. So you can think of the Fibonacci sequence, for example, as just a function where you're plugging in 1, 2, 3, 4, etc. And then the output of the 1 is going to be the first element. The output of the 2 is the second element. The output of the 3 is the third element. The output of the 4 is the fourth element, and etc. And so you can think of the Fibonacci sequence as a function where if you plug in 1, you get 0, plug in 2, you get 1, plug in 3, you get 1, plug in 4, you get 2, plug in 5, you would get 3, plug in 6, you would get 2 plus 3, which is 5, etc. So you can actually think of sequences in that way as well. So at the end of the day, a sequence is just a list of numbers in a definite order, meaning there's some rule or formula in the background for which I can come up with this list. The elements in the list, these are called the terms of the sequence. They can be represented by a letter with a subscript that denotes the position of the element. And the entire sequence will be that letter with like a generic subscript like N or I or J, or we do some letter, and it will be in squiggly brackets. And this is indicating to the reader, oh, we're talking about a sequence now. We're talking about a list of things. And this is all it is. Now, there are some important concepts that we want to be able to talk about sequences with. Like, it'll be important for us to know, for example, when does a sequence, quote unquote, converge? So we can actually talk about such a thing as the convergence of a sequence. Now, this is only applicable for infinite sequences. You can't talk about the convergence of a finite sequence. It doesn't really make sense to talk about that. But we can talk about the convergence of an infinite sequence, right? And at the end of the day, this is kind of like us trying to describe, if we go on forever and follow this list, does it follow a pattern where we can kind of just eventually have some sort of stability to the sequence, and we can actually describe it by how the tail end behaves, right? So that idea is captured by the notion of convergence. And it's actually done by doing a limit. So once you can figure out your sequence as a formula, what you can do is now you can take a limit. You take the limit as n goes to infinity. It's always going to be as n goes to infinity. And if you get a number as the answer, you can say that the sequence converges to that number, right? And if no such number exists, you would say the sequence diverges, and including if it goes to plus or minus infinity. So this is saying that you would say the sequence diverges to plus or minus infinity in these cases. So you can describe a sequence with a formula, and if you take the limit of that formula as n goes to infinity, if you get a number, you can say the sequence converges to that number. Now, because we're always talking about the limit as it goes to infinity, by the way, this is a definition that I do want you to remember, right? Because that is something that you will need to know. Like, does the sequence converge? What does it converge to, etc., right? And so I can also make the statement, it is always the limit as n approaches infinity, right? No other limit as n approaches some number will make sense. And we'll talk about why that is the case. So a sequence is just a list of terms in a definite order, a list of numbers. The idea is there's going to be some formula or algorithm in the background that is describing to me how to write down this list of numbers. Once I have that formula, I can examine it with a limit. If the limit gives me a finite answer, I can say the sequence converges to that number. If that is not the case, I say the sequence diverges. And the limit is always the limit as n goes to infinity. It doesn't make sense to say, for example, what is the limit as n approaches 5 of this sequence? It doesn't make any sense to say that. And we're going to talk about why that is, right? Because the sequence is kind of just like a discrete list of things, right? There's like a first guy and a second guy and a third guy, and there might be gaps in between them, and limits, you can't really have gaps. We're actually going to see how that works out in a little bit. And another way you can actually say this is you can actually just use this notation, AN arrow L, and that will be to say like your sequence converges to L, or to say the limit as n goes to infinity equals L, you can say your sequence converges to L. Or sometimes because it is understood that it's always limit as you're going to infinity, oftentimes myself and others will be very sloppy and not even write anything under the limit. We'll just say limit of AN equals L, because everyone kind of knows, oh, he's talking about an infinite limit because it's series. So you'll leave out the n goes to infinity part. And these all say AN converges to L. Right, so that's just the mathematical notation, the way that you'd actually write it down. Right? So you can have a sequence with which is a list of numbers, can describe it with a formula, and if you can do that, you can do things like examining it with a limit. And if the limit exists and is a number, you can say the sequence converges to that number. This list converges to this number, and that just means the limit exists and it is a real number. Okay. Any questions on the definition so far, like what a sequence is, what it means for a sequence to converge? Are we okay with that? Now, generally finding the formula can be a little bit annoying, but at least you should know that idea that, you know, a formula exists somewhere and our algorithm exists somewhere where we're getting these numbers from. They're not completely random. Okay. And sometimes it helps to think of sequences as functions. And that's useful because we can actually start to graph stuff, and you can get a lot of intuition from looking at the graphs. So let's actually look at one example, right? Determine whether the following sequence converge. If so, to what? And I'm going to illustrate with a sketch so you can actually see the idea. So here's a sequence. It's an infinite sequence. N goes from 1 to infinity. And it's defined by this formula, AN equals 1 over N, right? So, i.e., what am I saying? This list, it follows this formula, 1 over N, where N starts at 1 and it counts up by integers. So it'll start with 1 over 1, then 1 over 2, then 1 over 3, then 1 over 4, then 1 over 5, etc. Okay. And this will go on forever. That's the pattern. Now, if I were to ask you, does this sequence converge? Is the answer yes or no? What would you say? Does this converge, and what does it converge to? And remember the definition of convergence, it's right here. What would you say here? Does this sequence converge?
It converges to 0.
Converges to 0 by this definition. How do we know it converges to 0? Well, you just take a limit. If I look at the limit of AN, this is just going to be the limit of 1 over N, because that's the formula. And I know what that is as N goes to infinity. That's just 0. So I can say the sequence converges to 0. And that's it, right? Now to illustrate with a sketch, like when you think of it as a function, this means you can actually do a sketch to kind of look at what this guy would look like, right? So let's say I plot an as the output, right? Because that's the output of the function, like y. And let my x would be n, right? So I can have n equals 1, n equals 2. That's not to scale there, really, is it? N equals 1, n equals 2, n equals 3, n equals 4, n equals 5, and it goes on, right? And I can actually plug into this formula and get an output. So when n equals 1, I plug into the formula 1 over 1, I get 1. So it starts here, it starts at 1. And that is the first point. So n equals 1. N equals 2. Well, if I plug in 2 into 1 over n, I get a half. So there's going to be a point here, going to be a half. And 2 is all the way up there. That's that point. 3 is going to be a third. So I'm going to come down here. That's a third. So 3 is going to go up to like that level. And that's going to be the output there. Then I can have like a fourth. It's going to be like here. Then I can have a fifth, etc. Now, if you look at what these points are doing, obviously there's like a trend, right? So if I follow the green line, the green is kind of a trend. And if you kind of connected all these dots together and try to figure out what is a pattern that they're following, like in a trend, can I talk about some sort of stability? The answer would be yes. This trend is tending towards 0. It keeps getting closer and the points will keep getting closer and closer to the horizontal axis. They'll never actually touch it, but that is a description of where they're kind of trying to stabilize. So at one point, you start at 1, then you go to a half, then you go to a third, then you go to a quarter, then you go to a fifth. But the points all keep getting lower and lower and lower. How low will they get? How low can you go, right? 0, right? Now you'll never actually make it there, but you keep getting closer and closer and closer to 0. So we can say these sequences converge to 0. This sequence converges to 0. Now, you can also see from this diagram, because the actual graph is just isolated points, right? So like this, this broken green line, this is here is like the trend, but it's not the actual graph. The actual graph are these points. And in this picture, you can kind of see why it wouldn't make sense to talk about any other limit. Like if I were to say, what is the limit as n approaches 2? Well, how are you going to approach 2? For a limit, you need to get closer and closer to 2 from the left and from the right for that to even make sense to talk about. But you can't get closer and closer to 2, arbitrary close to 2 from the left and the right, because 1 is way over here, 1 unit away, 3 is way over here, 1 unit away. You can't get closer than 1 unit away from any particular number in this sequence. And so to talk about limits doesn't make sense when approaching any intermediate or finite value, because you can't get close enough for a limit. But your limit can describe like how you behave on a tail end. As you go far out to infinity, are you settling anywhere? A limit can answer that question. But you can't actually talk about a limit at any other point because there's a big gap between every point. So if you were to draw a graph of a sequence, like you wouldn't be able to actually, you wouldn't be able to take a limit at any point of that because there's gaps between all the points. So there's that. So that's an example of a sequence that converges. Now, what if I talk about this sequence here? That says C. There was another example, B. I don't know where it went. but let me actually write it in. So my example for B was just the sequence n. And goes from 1 to infinity, given by an equals n. Now, if I were to ask the question, does that converge? Well, you can take the limit of an. This is just the limit of n as n goes off to infinity. Well, that's infinity. So I can say here, an diverges. I can specify to infinity if I want to, but don't necessarily have to. And in this one, if you look at this picture, you know, I can do like a 1 and it goes to a 1. If I do a 2, it goes to a 2. If I do a 3, it goes to a 3, right? Etc. Right? If I do a 4, it goes to a 4. And so the trend for this one, notice that it keeps going upwards. So I can talk about a trend here, but it keeps going up and up and up. So like the terms keep getting bigger and bigger and bigger. They do this without bound. It'll eventually get bigger than any positive number you tell me. The terms of the sequence will eventually get larger than that. So I describe that by infinity. So it diverges off to infinity. Right? I want to consider this as divergence. Right? A third example. -1 to the n. So what does this actually look like? Well, this means your an looks like -1 to the 1. Then it goes -1 to the 2, then -1 to the 3, then -1 to the 4, etc. So this here gives you what's called an alternating sequence. So in this case, -1 + 1 -1 + 1 -1 + 1 forever, right? Now, if you were to take the limit of this guy, this is the limit of -1 to the n. Now that limit does not exist. And so we can say an diverges. Now you can't say diverges to infinity because it doesn't go off to infinity. If you look at the picture here, what happens is at 1, it's -1. At 2, it's +1. At 3, it's -1. At 4, it's +1, etc. So there's like a trend in the top and a trend in the bottom. But otherwise, this keeps alternating. It bounces up and down. So you can't actually find a limit, right? You can't say the limit is 1 because if you move a little to the right, it eventually becomes -1. You can't say it's -1 because you move a little to the right, it becomes +1. So it bounces between plus or -1. It never settles anywhere. There's nowhere I can say we have like a stability, and it's just a single number. So this also diverges. And it diverges for, it doesn't diverge to infinity. It just diverges because we can't get it to settle anywhere. So now if we look at this example. Now, we don't really have time to get through this example, and we have some more stuff I want to talk about. It's not a lot, but it's going to bring us over time, so I'm not going to do it. So I actually want you to try this example, but because there's potentially something here that you don't know, so I should probably tell you. This thing that you see in here, and with an exclamation sign. Anyone knows what that's called?
Factorial.
Yeah, it's called n factorial. It wasn't me getting excited or shouting at you, n, like that wasn't what it is. It actually means something mathematically. It means n factorial. N factorial is defined for all integers 0 and above. And the idea is the following. If n is an integer, then it's n factorial is really the product of all integers from 1 up to n. So this might go down to, say, 3 times 2 times 1 for n a positive integer. And by definition, you might wonder what would happen if n equals 0. We can talk about this. 0 factorial is also defined for us. We will define it to be 1. So an example here, if I write down 5 factorial, this just means 5 times 4 times 3 times 2 times 1, which is 120, for example. So when you see this notation, the exclamation sign, it actually means something mathematically. It means, for us, like when you take a complex analysis course, you can define this in general with something called the gamma function. But for us, this is only defined on the non-negative integers. 0 factorial is 1, and then you can have any integer factorial, 1 factorial, 2 factorial, 3 factorial, 4 factorial, 5 factorial, 6 factorial, going all the way up. Now 0 factorial is 1. For any other factorial, the factorial is defined to be the product of all integers from 1 up to that number, right? So 10 factorial is just the product of numbers 1 times 2 times 3 times 4 times 5, all the way up to 10, right? 5 factorial is 1 times 2 times 3 times 4 times 5, etc. Right? So with that in mind, I want you to examine this guy. Tell me if he converges. And if he converges, tell me he converges to what? Based on this, this idea here. So we will stop there, but we've almost finished with this section. Like the first section in sequences and series is just this. Like you need to know what a sequence is, what it means for it to converge. We need to talk about some basic properties and some new kinds of functions like n factorial. And also we need to know about when a sequence is increasing or decreasing. But other than that, once you know these definitions, we can actually move on to bigger things. So there's actually a lot to talk about when it comes to sequences, but we're only covering enough, all the things we need to be able to talk about series, right? So we're covering enough of sequences to talk about series, because sequences are going to be very useful in discussing series. That being said, we will end here. Remember, you should be able to log into Gradescope already. So the email for Gradescope went out a while ago, like the first day of class. So you should, first of all, check that you can log into Gradescope. If not, email me and tell me that you can't. And second of all, if you do log into Gradescope, you should already see the first practice test. You can start whenever, up from now until Thursday at 6. Hopefully you do it earlier than Thursday at 6. It's not timed, despite what the instructions say. But I will be uploading some more practice, maybe 2 or 3 more practice problem sets that will be timed to have you see what's going to happen and get a feel for it. That being said, it's late. So let's actually get out of here. Thank you for your time and attention. Have a good night, and I will see you all in the next one. Ciao.